Okay, so we will be, today we shall be discussing about the learning aspects in controller design. But before that, let us understand what is machine learning. So today's lecture is devoted to machine learning, right? So just a minute. Sorry. Can you see? I hope you can see my slides.
Yes, ma'am, it is visible.
Yes, ma'am.
Thank you. So we begin with a very brief introduction to machine learning today. And then we will move on to introduction to neural network, because neural networks are dominating the scene these days. They are the basis for deep learning, which is the current trend in machine learning. So what is learning? When we talk about learning, so you know that I say that a child has learned very well. Why? Because by showing him some examples of, say, flowers, he's able to understand that what kind of object is a flower. Similarly, if I give him some examples of colors with different balls of different colors, he will be able to identify. He's able to identify shapes quickly. So learning denotes changes in the system that are adaptive, in the sense that they enable the system to do the task drawn from the same population more efficiently and more effectively the next time. What I intend to say that, suppose you give 4 examples to a child of all round shaped objects. First time he may not be able to identify that all are round shaped objects, but next time he will be able to tell in a better way that yes, these are round shaped objects. So think of your school days when you were doing mathematics. So first time, second time, some people are able to immediately grasp the concept and are able to solve the mathematical problems or numerical problems very easily. Some take a little more time, but that process of taking time to understand the pattern so that we can solve a problem, we can recognize a color, all this is a part of learning. So what is machine learning then? So machine learning, as we all know, is a field of computer science that gives the computers the ability to automatically learn the patterns without being explicitly programmed. You have been listening to the lectures of Professor Beng, and you see that for a simple system specification with only 3 states or 4 different types of states, some forbidden states, some reachable or unreachable state, you have to actually create the logic for each and every state so that you never enter into a deadlock or a live lock, or you are able to do the given task, you are able to reach the given state, that is desired state, right? So a lot of logic is required, and that requires to, that needs to be programmed very thoroughly stepwise. Similarly, planning, you have to do a lot of planning to define the logic, to execute in each and every step. Now, all this would have been easy for us if we say that, okay, I give the input and I give the desired output, and the system is able to understand through some examples that, okay, if this is the input, I should be giving this output, right? So it is what it is the understanding. It is trying to understand the patterns corresponding to each input pattern so that it can map it to an corresponding output or desired output pattern. That is what is known as automatically learned without being explicitly programmed. So learning from the experience on data, the input output data, to make any predictions so that it is able to behave in the way, the system is able to behave in the way the user wants. So basically, machine learning is a branch of artificial intelligence, which is concerned with design and development of algorithms. We saw several examples of algorithms using predicate logic, using mu calculus, using the graphs and all those things that you saw. It was a finite state machine or automaton. That what we are doing is we are building the algorithms so that the system is able to perform in the desired way. So here, in case of learning, because systems are too large, there, as you know, there can be billions of states between two different inputs and outputs, right? And handling those billions of states, and if even one single state is left, I mean, somehow missed, then the system falters, right? Although many of them are redundant states as well, so that there's no failure, like so that there is a dependable kind of system. So here, machine learning deals with design and development of algorithms that allow computers to evolve behaviors by experiencing the data. So if I have data, I'll later talk about what kind of data are available. But let's think that we have a data, and that data is having two different types of elements. One is input, and the other is desired output or expected output. So suppose you have data, and the data contains, say, some 200 examples of data, right? What we do is that we take quite a few examples from that. For example, you can take some 150 examples out of those 200, selected randomly, and then put them to machine learning algorithm. Like you feed them to machine learning algorithm. So if I have data, let me take this. I have 200 data samples, right? I split them into two parts, like 150, that is 75% of the data, and then 50. 50 I will not be using for now. I will be using 150 samples and will feed this to machine learning algorithm, right? During the training period. I will, and suppose you have an input is X, the output is Y. For each value, for each sample, I have the value of X and I have the value of Y. This value by value, I don't mean just one single value. It can be the entire vector or an image, whatever you want. You can have an array. So this can be X, and the corresponding Y can also be just single value or number of states or array, right? Whatever you, depending on the application that we're using. All right. So this machine learning algorithm will be taking, so this X will be input, right? And we will be expecting the desired output, right? So X1, Y1. But output, it may not always give the desired output. It may give Y1 prime, right? It may give a different output. Santosh wo bhi le jana. So it may give a different output as well. Okay. Now the question is, so suppose a child is expected to learn different colors. So suppose there are 3 different colors of balls that are shown to a child. And there are plenty of examples, like 50 examples of balls. And each time you give show in your hand, what is the color of this ball? The child will say yellow, green, blue. But then the actual color may not be yellow. So it is making an error, right, in prediction of the color. So that is what I'm saying. So suppose the input is, say, number 2, and the output turns out to be 2.5. So there is an error in approximation or error in prediction. So what I intend to say here is that suppose the system is able to show an accuracy, that it is accurately able to predict Y up to, say, so 80% times it is able to predict correctly, right? Let me start with a very low accuracy. So let's begin that. Okay, first time I've shown the data, it is able to clearly identify only 30% Y values. It is very close to the Y value. It's having 30% accuracy in predicting the Y values, right? I will show again this data 150 data. I will show again to the machine learning algorithm and telling it that you have made these many errors. For this Y value, which is 2, you have made an error of 0.5 by predicting it to be 2.5, right? If it is 3, then you have predicted it 3.7 or something. So next time, by looking at its own error in understanding the pattern, suppose it is able to predict 50% correctly, right? I will again show the same data to the machine learning algorithm. And next time, perhaps in this way, I will keep on doing this. And after a number of iterations, which we call as epochs, right? After a number of iterations, suppose it is giving you some 95% accurate results. So I'm happy with the performance of the algorithm based on the application, this 95% accuracy or any other kind of measure that measures the performance of the machine learning algorithm that you can use and see, okay, if my algorithm is doing better, I can deploy it to the real life application. But before deployment, you would like to further test whether on unseen data, these 50 samples that we have kept separately, on these unseen data, how this is behaving. So I'll ask this, I will input this to machine learning algorithm, and maybe it is also able to give some 94% accuracy, suppose. So I'm happy, okay, on these 50 unseen samples also, it is showing a good accuracy. Now my machine learning algorithm is deployable. So I will deploy it to a real-time application, real life application, and then the data that will come will be totally unseen, right? So this totally unseen data is known as test data. This data consisting of 50 samples is known as validation data that you use to predict, to check whether my system is actually doing well on unseen data or not. So this will be the test data. This will be the train data, This will be the train data. And this 50 samples will be the validation data, right? So what I intend to say is that whatever data that you use in the lab for building your system is either the training data or the validation data. The real data, which comes from the real life application, is the test data, right? So once your test data is available, the trained model is deployed, and it is performing with almost similar like 93 to 95% accuracy, you are happy that your model is performing well on the real life application. Think of an autonomous car. You have designed a controller for autonomous car with the help of machine learning algorithm, and your autonomous car works well in the lab, right? You now take it out to your campus, institute campus, and you run the car in the institute campus. It is performing well. It is identifying objects, obstacles. It is accordingly escaping from the obstacles, and it is able to reach the destination. You're happy with that. And finally, when you run it on the road, there can be many unseen obstacles, like a moving cow in typical Indian village roads, or even small city roads, which may not be there inside your campus. So if your controller that you have designed using a machine learning algorithm for the autonomous vehicle is also able to perform equally well on these unseen data, then you say that, okay, my autonomous car is actually ready for deployment, right? So generally cars are first tested on the test beds, and then they are deployed for the real life applications, right? So it is something like that. Please feel free in asking questions if you have any. So there are, one is testing, training, and the other is testing. So there's something which we call as a universal set, where you have a lot of data available, which is like, which the system might not have seen while it is getting trained. The machine learning algorithm might not have seen while it was trained. So what we do is that you have an universal data. Let's take an example of designing a CAD/CAM system, computer-aided diagnostic system, which is diagnosing, for example, some cancer cells, right? Now, whether the input sample it can be an image, it can be any other thing. So it is looking at some cancerous elements which are present or not through the input. Now, there can be many people who are normal and who are suffering from cancer, but we don't have data of all. We will be having data of, say, some 2,000 people who are normal and whose normal data is available, and there can also be people who are suffering from cancer. So cancerous cells are present. So we sample from that data, and then we identify through a machine learning algorithm the patterns available in the data that distinguishes them from cancerous and normal cells, right? Normal people. So then this is done, this is a training set. Machine learning algorithm is given experience on this training set, and it learns to identify cancerous and non-cancerous. And then once it learns, it is deployed in the real life application for solving real world problem. And then this CAD system may get in future some new samples which it may correctly or incorrectly identify. That is what is known as training and testing. Prediction, we expect it to do the correct prediction for each case. So training is the process of making the system able to learn, right? All right, so a machine learning algorithm is an algorithm that is able to learn and extract patterns from the data. What is learning? I say there is a definition given by Michel in 1997 of a learning. We say that a program is set to learn from experience E. Experience on which? Data. Experience E with respect to some class of tasks T. Class of tasks can be identifying whether it is cancerous or non-cancerous, normal. Identifying if there is an obstacle in front of an autonomous vehicle or not. Identifying whether I have to turn right, turn left, something like that. This can be some class of task for different kind of algorithms, right? For cancerous, there will be, for cancer cell identification, there will be a different algorithm. So there can be various class of tasks. For example, in autonomous vehicle, there can be different tasks. Task can be identifying the street signs, road signs, identifying whether the road is clear or clean or not. If there are obstacles, there can be many tasks. With respect to some class of tasks and performance measure P, right? Measure can be accuracy, measure can be different type of precision, any kind of measure depending upon the task and its performance. I seek your attention, please. And its performance at task T, as measured by P, improves with experience on D. That means I told you that first time I gave the data input, it gives only 30% accuracy. Next time, 50%, next time, 80%, and so on and so forth. Ultimately, it reaches 95% accuracy. So the task was the same, but performance was increasing. So learning algorithms can be broadly classified into three different categories. One is supervised, the other is unsupervised, and the third is reinforcement learning, right? So supervised, I just gave you an example that I have X, right, and the desired output Y. These Y are known as labels. I have dot X, data X, and the desired output Y. That is the label. So I have data with label. I input that data with label. That means I am giving it a hint that this is the expected output. You are expected to give this output, right? That is why it is known as a supervised learning. It gives output. As a critic, I give that you have made errors. These are the errors. I give the feedback, and that feedback is then taken as an input along with the next time when the data is input to the algorithm. So this is what happens in case of supervised learning algorithm. In case of unsupervised learning algorithm, data is given, but there are no labels, right? So like suppose a robot has to explore on the moon. It may not be having any information about what kind of objects are there on the moon's surface, right? So in that case, it will be getting inputs, which will be images from the infrared or from the optical signals, optical sensors, but then it will be collecting data and it will be learning the patterns of the data depending on the input that it has. So it segregates that, okay, these are all similar type of data, and then you get suddenly a different type of data input. So you put them in a different category. So these data without labels are given, and the system is, the algorithm is expected to learn the patterns and segregate the given data into different clusters. That is what is expected in unsupervised learning. All right, then you have reinforcement learning. Reinforcement learning, on the other hand, depends on certain depends on the environment. There can be an agent which is taking some actions, and based on the current state and the action, what happens that either the agent is rewarded or it is penalized, right? For example, if you have to come to a campus and you have been given the Google map. Now, sometimes Google map gives you the shortest distance, and that shortest distance can be a very traffic high, can be a high traffic shortest distance. And suppose you enter that shortest distance and you realize that you have entered in a wrong on a wrong path, and you would like to take another turn. And suppose you take a turn which is leading away from the campus, institute campus. Then what does that mean? That means you are based on your action, you have got a penalty because you are getting away. So you will have to spend more fuel to reach an institute campus. So what I intend to say that reinforcement learning again is based on the current state, the action, the past experience that I have with respect to the environment, and based on those actions, some certain tasks are to be performed. The task could be reaching a goal state, and that goal state can be reached using certain rewards or penalty. We'll be Professor Beng will be telling you more about this in a later lecture, right? Now, so then there is something called semi-supervised learning, which is which is a hybrid of these two types of learning, unsupervised and supervised, where only a very small amount of data is labeled, the rest of the data is unlabeled. Okay. So supervised learning means what? Observing sufficient number of examples from a random vector X, right? Because these samples are randomly collected from the entire population. And so population doesn't mean here always a human population. Population can be the population from the different possible states, can be a population. And an associated label Y, either an expected value or a vector. A label can be vector also, can be associated value, expected value also. And learning to predict Y from X. So supervised learning means it learns to predict Y given X. That means it is estimating the probability of Y, happening of Y under the condition X. It is known as the conditional probability of occurrence of Y under the condition that X has occurred. So example, suppose in a wind turbine SCADA system, there are lot of SCADA system right now. And so there is a LV, you can say that it records some low voltage active power, wind speed, wind direction, but it has also been given theoretical power curve, right? So made by, as specified by the turbine manufacturer in each interval of 10 minutes, right? So in each interval of 10 minutes, it gives you an output of active power in low voltage active power in kilowatts. It has got some reading of wind speed, wind direction, and the SCADA system also has the record that theoretically the average power should be lying between these values and that values, like the average value is given, right? So the active power should not be so much deviating from the average power under the condition that the wind speed is this much and wind direction is also that much degrees of wind direction, right? So this is the example here. So after having enough example from the SCADA system, the program learns to predict the system behavior and detect if there is any anomaly. So suppose suddenly there is a loss in the active power value, or it is going away from the average. So there must be something which is not expected. And so SCADA systems help identify those anomalies, and in all the power grids, you will find SCADA systems are available. So these are basically SCADA systems are supervisory control systems for which are used in wind turbine or power grids or electricity grid. So supervised learning means that you have data. That data can be text, document, images. It can be sound. It can be, say, voice signal. It can be, say, ultrasonic signal, any kind of signal. So from here, what we do is that we first, from each data that we have, data sample, we identify the feature vector from the data. We extract features from the data. Those features we supply to the machine learning algorithm as input, along with the labels. Machine learning algorithm learns to identify the pattern and it predicts. So once it is ready with the training, it is new data is given with the feature vector. The predictive model is ready and it gives the expected label. That is how it happens. I hope this is clear to everybody. Please say yes or no on the chat box if you have understood it or not understood it. I request you to please say yes or no. Write yes or no on the chat box. Yes, Amir, you're already doing the Pujwal, thank you. Manbir ma'am, yes, thank you. Anyone who has not been able to understand, please feel free in writing. RD, thank you. Thank you. Thank you so much, all of you. Okay, so let me go ahead. So unsupervised learning. Unsupervised learning is a little different concept. Here we have sufficient number of examples of random vector, but we have no labels. And idea is to implicitly or explicitly learn the probability distribution of X. That is from where this data is coming. What is the distribution of the data? For example, I will say that by and large, almost every day, say some 329 kilowatt of power is being generated, right? So every time, every 10 minutes interval, I will be getting 329, 323, 324, but I don't have any idea of what is the manufacturer's average for this kind of wind speed and with this kind of wind direction. So I will be attempting to find out as an algorithm, I will try to find out that, okay, if this is the wind direction and this is the wind speed, this should be the output, the corresponding output of the active power, right? This should be the, sorry, of the wind turbine. So what is intended here, that I have no idea of what exactly would be the power value, but I will, by looking at the number of times the data, I will be able to identify that, okay, for these two features, that is wind turbine, wind direction and wind speed, the power value should come to somewhere around 320 to 330, that's all. And if the wind direction is, say, for example, of a different direction and different speed, then the power value should ideally be somewhere between 320 to 310, right? Or it can be very low power value. That is how the power values are segregated for different types, different clusters of inputs of, different features of wind direction and wind speed, right? So this is known as unsupervised learning. Since there is no label attached with the random samples, the algorithm must learn to make sense of the data without any guide, and that is why it's called unsupervised. Let's take an example of cluster of cells in a given image sample to identify features that classify cancerous and genuine cells, as I told you. So here you can see exactly the same thing, but there's something missing here, which is this label. Label is missing, right? Now, reinforcement learning, what happens that there is an environment. Based on the environment, and I may be having the previous knowledge of the environment or experience of the environment, I take some, and so I have the state, the current state, where, for example, if think of a robot which has to complete a task standing on one corner of a shop floor in a manufacturing shop, in a manufacturing company, and suppose it is it has to do some task. So based on the task that is given to it, it will be changing its position from one position to another position. So it will be changing its state. When it changes its state, it either turns left or turns right or goes straight. It is going closer to, say, the location of the task. The task could be picking up some object. So it is either going closer to the task or it is going away from the task. Accordingly, so each action will lead to a reward. So you can see here that at this different time intervals, you have a state, you have an action, and the corresponding reward that can be positive or negative. I'm now in a different state. I apply another action, I will be having another reward, and so on and so forth. And ultimately, by accumulating these rewards, I'm able to reach I'm able to achieve the goal, or I'm able to complete the task. So RL deals with agents that must sense the state of the environment and take appropriate action to fulfill the objective. The current action influences the state of the world, which determines its reward. And it learns from the interaction with the environment to achieve a goal. So what happens that it is learning from the interaction, from interaction with the environment to achieve a certain goal. You must have seen several games which are very much popular in the world. These video games or these important computer games, many of them are based on reinforcement learning, and you get some rewards, you get some penalties when you are using when you are running those games. Well, so whenever there is an algorithm, there must be, and it is performing some job of identifying or understanding the pattern, there must be some methods by which we measure the performance of the algorithm. So there are several factors that affect the performance. First, for example, what kind of training is provided? Is it unsupervised learning or supervised learning? If it is supervised, somebody is being trained in a school, right, by a teacher. So he gets an environment to learn quickly, and somebody has to explore himself. He will also learn very well, but then he may take some time. So what type of training is provided, right? Well, within the training itself, there are many things that affect the performance of the algorithm. We will come to know later about it. The initial background knowledge, the extent to which it was made available to the algorithm, right? Background knowledge. Like, for example, as I told you that apart from label, there can be some background information that is available. Like, for example, if you have to cluster the given data into different groups, then clustering can knowing that how many groups are there can be helpful. Like in k-means clustering, number k is specified prior to running the algorithm, right? So that can be a background knowledge. The background knowledge can also be like, suppose you are making a controller for the autonomous vehicle. The background knowledge can be like, what kind of roads are there? What kind of road signs are there? What kind of facilities are available for refilling the fuel? All these things. The type of feedback provided. In case of, that the type of feedback, in case of supervised learning, in case of reinforcement learning, both cases you have certain feedback. And the data set size and quality, the more data you give with a variety of data, it will be able to learn quickly. Suppose, for example, you give the same type of numerical problems to your students, to a student, and there is no diversity in the level of difficulty in the problem, the student will not be able to learn better. But if you give diversity to a student to learn in the problem, it will learn better. So not only that the number of examples are important, the quality of the data is also equally important. The learning algorithms that we use. So two important factors are there, modeling and optimization. See, modeling your excuse me, hello. So modeling means how do we model the entire problem is important, right? We have, accordingly, we'll be able to design. And for this, you saw, we have been talking, Professor Beng has been talking about different types. How can we understand and model exactly, accurately the given problem or the task. And optimization. How do we optimize the algorithm to achieve its goal or to perform well? Right. So the main objective of supervised learning is to minimize the average of error in finding Y for each sample X. More precisely, I will say that suppose measure of the distance between Y and Y of Y hat. Then what is Y hat? Y hat is predicted value, and actual value that we call as ground truth is Y for each sample X. Okay. So as I told you, the predicted value of the power and the actual value of the power, right? They can be two different things. And if we see that, okay, my system is performing exactly like my machine learning algorithm is performing very close, and this error in the measurement of these two values, the distance between these two values is negligible, then I can deploy my algorithm, right? So let's take this example of you have X and the corresponding Y. This Y is like yes or no, 1 or 0. So, and suppose Y hat turns out to be 0.99. Yeah. So Y hat for this Y, this is the input features which are given 1, 2, 3, or input sample which is given with 3 features or 3 dimensions. And then the output turns out to be 0.99. There is an absolute error of 0.1. Similarly here and here and here. So you get error values, and then you take the average error by taking the sum of these errors and dividing by 4, because there are 4 samples. So mean absolute error will be 1 by 4, the sum of Y minus Y hat for all these 4 values. I varying from 1 to 4. I should have written here I, Yi, this is Yi and Yi hat, right? Is equal to 0.24. So this is mean absolute error, right? So the objective is to minimize this error in case of supervised learning, right? In case of unsupervised learning, to measure how good is the approximation of the probability distribution. So let us take this example of blood test report of 1,000 patients, right? Based on certain features of the blood samples to identify whether the patients are in some category, right? So it can be COVID affected, malaria affected, typhoid, viral fever, none of the categories. So there are, say, 5 clusters, 1, 2, 3, 4, and 5 clusters in which your algorithm is supposed to put those patients' blood samples in these categories, right? But it's not necessary that the diagnosis is correct. So diagnosis is maybe wrong by the system, by the algorithm. So the basic idea is to minimize the diagnostic error here. So the number of samples which were actually misclustered or classified is the error that shows, right? So not always the samples are known to be of that that category. So what happens here? For example, if it is a clustering problem of clustering the given samples into 5 categories, then what we do that, suppose there are clusters, right? These clusters, and then you have, I use a different color. Then you have different clusters, right? This is the second cluster. The third cluster is suppose cluster here, right? Like this. So sorry, samples are given of this type. And now I cluster them. So when I cluster them, I segregate these blue separately. I will call them, right? These are separately. These are into one cluster. And then while doing it, I might have made some mistake, and I put one pink colored object also in this. So this is my cluster 1. Similarly, in this cluster, I have here, and by mistake, I have put 2 blue color samples here. So this is my second cluster. And similarly, the third cluster. So what I intend to say here is that the clusters which are made correctly or not is identified by looking at the features of the cluster, features of the samples, and looking at how distant these features are. So the intra-cluster, within the cluster, the distance between features of 2 samples should be small, and between 2 different clusters, the distance between the features of these samples should be large, relatively large. That is the idea. So here you can see that because this is pink and this is blue, the distance between these 2 features is large, whereas they are inside the same cluster. So the intra-cluster or inter-cluster, intra-cluster distance should be small, and between clusters, distance should be large. That is the basic idea. Now, before we go ahead and I take a small break, I would like to just, if many of you might have already done a course on machine learning, is just remind you of some important terms, right? Brushing up of our knowledge. Generalization. What do we call as a generalization? Is the ability to perform well on previously unobserved data. That is test data. It should be able to perform equally well as it was able to perform on training data, right? Or validation data. Training error. The error observed on training set, test error, or generalization error is the expected value of the error on an unseen input data sample or a set of unseen samples, right? What is underfitting then? Underfitting basically is when your machine learning model that you have made is not able to obtain a sufficiently low error value, or it is not able to perform sufficiently well on the training set, that it is not able to recognize the patterns in the data very thoroughly well, then it is known as underfitting. Overfitting, when the gap between the training error and the test error is too large, then you call it like overfitting. Like suppose it is giving you an accurate result for all training data of 95% accuracy. Mean accuracy is this. Or what, not mean accuracy, I should say accuracy here. Accuracy is suppose 95% in predicting the labels, why? But on an unseen data, it is giving some 74%. So there's a huge difference between the two. It's over, so it has overlearned the data samples so that it is not able to recognize any variations if that are possible within the data, right? Then regularization is any modification that we make in the process of learning to reduce the generalization error. Sometimes these modifications are made in the objective function, that is the error function. Sometimes these modifications are made in the process of training. Any kind of this is known as regularization. Let's take an example of an overfitting data. So suppose you took some samples from a data which was more like a sine curve data, sine curve, right? Signal was coming to you, which was a sine curve, right? And so you have taken data. So because you have taken data, there can be noise in the data. The system records the data. There can be noise. So it is not exactly falling on the curve, little away from the curve, right? These are the data samples. Now we wanted to know what is the behavior of the system. What is the function at any point of time, right? So I used a polynomial of very high degree, say degree m is equal to 9. A polynomial I'm using for approximation of the sine function. So what happens that it is passing through each and every point, like at all seen data, these are seen data, which are samples which are given to train. It is exactly passing through those data. That means there's no error in the data. But if I suppose I give another time, for example, I take a time like this time, at time t is equal to this, x is equal to this value. Now you can see that there's large deviation. So although this algorithm, which is creating this polynomial function, is learning very well on the given data sample, but it is failing to produce good results on unobserved data value. So how to prevent overfitting? Overfitting can be prevented by giving larger data set. That also sometimes helps overcome overfitting. Dropping certain hypotheses such as model capacity. I gave you an example of a high degree polynomial space. Classical regularization methods. For example, maybe when Professor Beng discusses on optimization, he may give you some examples of objective functions where regularization is used. And other methods include data augmentation, early stopping. Many methods are there. So there are unsupervised learning algorithms, which are very much frequently used, like principal component analysis, which is generally used for dimensionality reduction. Like if you have data with very large dimension and these many features of the data are all correlated, you don't need them to input to the machine learning algorithm. You can apply principal component analysis to reduce the dimension. Then there are generative models of neural networks, which approximate the data distribution density, right, function. Then we have clustering algorithms like k-means, hierarchical clustering, graph-based clustering. We have matrix factorization methods. These are all unsupervised learning algorithms. Supervised learning algorithms are like support vector machine. We have used you must have used it for your research and learning purpose, in learning. Linear regression, decision trees, artificial neural networks. So today we shall be talking more on artificial neural network. With this, I would like to give a small break and would like to ask you if you have any questions. Please unmute yourself. You can ask a question or you can write on the chat box. So we are 4-1. I will be back at 4-6. Thank you. Okay, so I'm back. Please feel free in telling me if I'm going slow or fast so that I can change my pace, right? So give me a minute. I have to connect it to charger. My laptop is showing low battery, right? Okay, so any questions you have till now? If you have any questions, please feel free. All right, so we go ahead with the artificial neural network. All right, so artificial neural network, as you may be knowing that it's an information processing paradigm, which is inspired by human brains. Human brain has neurons as the basic information processing unit. And these information processing units are working in unison to process the information and result in action, take a decision, right? So it is composed of a large number of highly interconnected processing elements, we call neurons, to solve specific problem. That specific problem can be any type of problem depending upon the application that we are for which we are developing the neural networks. So they learn by examples like human being. So if we look at the basic model of neuron in the brain, so it has got various receiving and transmitting units. And the main purpose is to receive signal, analyze signal, and transmit further the signal. The signal is carrying the information, right? So when a neuron sends information, we call that it fires, and it acts through specialized projections known as dendrites, axons, and it carries information throughout the neural network in human brain. It was in 1940s and 50s when the current modern neural network, studies on modern neural networks started in 1940s and 50s. Although in late 19th century also, like in 1880s or so, some people started building a mathematical model for neuron. But the current definition of, or the current model of neuron has its roots in 1940s, when people were working on connectionism and many important related concepts. So mathematical model of neuron is like this. You have information processing unit, which is this. It has got, it receives signals, like it has received 3 inputs. So it is receiving an input with 3 features, I should say. These 3 features, X1, X2, X3. It associates a weight to each input feature, right? So it associates a weight W1 to X1, W2 to X2, W3 to X3, different weights. And then it sums up the input, right? So it will be W1, X1 plus W2, X2 plus W3, X3, right? That sums up. It also uses its own bias in processing the input, right? So bias here, in a very crude way, you can say that every information processing unit has its own bias. This bias could be, for example, it can be liking, or it can be my understanding of something. So I always give this example, like some people would prefer light colors to wear on, and some people would like to prefer to use dark colors for clothes. So it depends on, like, all of us are having similar, like we have similar biological structure, but why do we prefer red over white, or why white over red? So suppose that every neuron has its own bias. So this bias is added, and then on this bias, an activation function is applied, right? So that is output from the basic information processing unit called neuron, and in computer science, we often call it unit only in place of neuron. So mathematical model is like this. Suppose you have an example, you have this x1, x2, x3, the corresponding w1, w2, w3 weights, weighted sum, and this weighted sum is here. I have not applied any bias here. So it's a w1 x1 plus w2 x2 plus w3 x3 is 4.1648. And then on this, I apply an activation function. Let me take this as the activation function. Sigma z is equal to 1/1 plus e to the power minus c. This is known as a sigmoid activation function, which is very frequently used. Why, we will tell you later. So mathematical model, how do we create? So you suppose you have a data set. Data set consists of 3 inputs, right? 3 input features and the corresponding label. That label is suppose showing the class 0 or class 1, right? Cancer, yes, cancer, no. Anomaly, yes, anomaly, no, right? Suppose like this. So train the neural network. Let's see how. So we initialize with random weights. So initialize, like each neuron here, these are different neurons. Each neuron will be taking the input, giving different weights randomly to different input parameters or different input features. So suppose there are 3 neurons and there are 3 input elements also. Not necessarily that you choose 3 only. You can choose any number of neurons here. They will be processing the input information, that is feature vector, and they will be, each of them will be independent in choosing their own weights. So because there are 3 neurons and there are 3 inputs, so there are, for each of the 3 inputs, there are 3 neurons. So you can see that there are, you will be having 3 cross 3, that is 9 weights that you will have to initialize. So initialize randomly the weight. Then I present a training pattern, training example, and feed it to the neural network, get an output, and compare it with the actual value. So how do I get an output? The moment I give this input, the information, this will be processed by the neuron, and it will give an output. That output will go to next level of neuron, like this black neuron, which is the output neuron, right? This will be given to this, right? All of them will be, all the 3 neurons will be sending to the next neuron. The next neuron will consider them as pure inputs and will also associate its own weight, say W1, W2, and W3, right? So, get an output and compare it with the actual value. So suppose this is given, these have processed already, suppose, and the output turns out to be 0.8. So this 0.8 is matched with this 0. So the expected output is 0. The actual output is 0.8. The error is 0.8, right? So what I will do, what can be adjusted? Only the weights can be adjusted because we randomly selected the weights. So the neuron thinks, okay, I should have given more weightage to X1 than X2 or X3. And the second neuron similarly thinks that I should have given more weightage to say X3, which I gave less. So it will adjust its weight. Each of these weights will be adjusted. And there is a process of adjustment, I will tell later. So error turns out to be minus 0.01, right? Okay, next time when I give the input to this, the next error comes out to be this. So adjust and update weight and present a training pattern and feed it to the neural network. And this process is repeated again and again till the you reach an error level that is below the desired level of error. Remember that here we are trying to minimize the error, but we are not saying that I'm optimizing error. What I intend to say is that I wish to make my system learn so that it is able to, so that the error does not exceed, say, 0.01 or 0.1, depending upon the kind of application that I've chosen. Okay, so mathematical model of this is like weight adjustment process is repeated thousands and thousands of times. And each time a random training example is taken, weights are slightly adjusted to tune the system for reducing the error of approximation. Well, you must be thinking it's not a very efficient adjustment. Yes, I agree with you that this may not be an efficient adjustment in many cases, but eventually what happens? The process of weight adjustment leads to a good enough model for producing an effective classifier. Why? The question is why? How do we guarantee that this will always happen? Is there any answer for that? Can you give an answer? Because theoretically, there are results on neural network that say that neural networks, yes, weight adjustment will minimize the error. I agree with you, but how they will minimize the error? There are methods which help minimize the error. And so what will happen that the next example that so Dr. Manmeer Kaur says that weight adjustment minimize the error. In fact, there are theoretical results also, participants that help us believe that, yes, this will happen, right? So eventually the process of weight adjustment leads to a good enough model for producing effective classifier. So it works well in many real time applications. And so I move on to multilayer perceptron with this theorem, which says that any continuous function over a compact domain can be accurately approximated using a neural network with one hidden layer only. There is a result by Sibanko in 1989. It was proved that any continuous function can be approximated. Dr. Manbir Kaur says that depends on the algorithm selected, like back propagation, using steepest descent technique. Yes, but ma'am, there are various issues, like how do we initialize our model's weight? Suppose I have got, let me take, right, so suppose W, these for one single W, I'm plotting this, right? All right, so what happens for error, the error function for one single W is here, right? So you will be, by steepest descent method, I will be able to reach the error very effectively, because I will go in the opposite of the steepest descent method. But if suppose I am, let me take this another example by saying, I am here again. The least, like the minimum here of the error function is here. I am here. I've taken a W value, starting W value like this. I applied steepest descent. Now, when I apply steepest descent, I see that, okay, if I go further, what will happen, that the error will tend to increase. So when you plot the error on the graph and in the practical implementation, you'll see that the error is going out. When the error with epochs is going up, you would like to stop here, right? So what happens that the problem with neural network is this, that it depends on so many values, W values, and so it is highly multivariate graph, and there are so many local minima, so many saddle points, so many cliffs in the graph of the error function, that reaching the point, the desired point of accuracy or the desired level of error is sometimes very difficult. And here comes the importance of different optimization algorithm that you might be, I don't know whether Professor Beng, what exactly is Professor Beng is going to cover, but he will be probably covering some optimization algorithms. Thank you. So if the theorem says that if layers increase, accuracy of approximation also increases. And to deal with non-linearity and better approximation of more complex functions, multi-layer perceptron models were introduced, where we had an input layer, an output or decision layer. Along with this, there was a hidden layer. Several hidden layers. So the number of hidden layers are large. We call it a deep neural network. So deep neural networks have a large number of hidden layers, in fact. Earlier, only 3 layers would be called 3 layers, 4 layers, hidden layers will be called deep neural network. But now, with the advancement of computing methods and computing devices, the number of data, the amount of data that is available, we generally consider them to be shallow network. They're not very deep network. So Madam Manbir told that back propagation of error by making use of some steepest descent. I told you that we adjust the weight. How do we adjust the weight? Let's see. So I've got an input layer. I've got some hidden layers. The information is processed, like those X1, X2, X3 with the weighted inputs are moved forward to each layer. And finally, they go to output layer. This output is compared with the correct answer, the correct label to get the error signal, right? Once I get the error, what we do is that we back propagate the error, not actually the error, but the gradient of the error, right? We back propagate the gradient of the error to help reduce the error. I will show you how, right? So I do not, so let's see. All right, so suppose your error is only one-dimensional and it is like this, right? Error function. All right, so it has got, suppose I consider this point, the current value of W, because the error will depend on the random weights that we have chosen and the biases. So suppose for a given W, the error is this much, right? Now, I have to go in this direction. What is this direction basically? It is opposite of the direction of the gradient, right? Because gradient will always point to like increase, the highest, the maximum, right, value. It will give you the maximum value, the rate of change. I will go in the opposite of the gradient direction. So I will go to a minimum direction. But by what amount I should step down so that I do not reach a point. Suppose if the gradient is suppose very high, large, I will go this way, and it may happen that I end up, the corresponding value of the error is this, right? So I end up at a point W for which the error value is this much. This is the error graph. This is the corresponding W. Now, next time, if I take this and suppose I go to a different, like take the gradient value. So the corresponding, this is my W value, and the corresponding error value is this, right? Error value is this. So what I intend to tell you here, my dear participants, that we take us, when you are going down, you take a small step, right? So I make use of steepest descent method, which is iteratively going closer and closer to a minimum value. So instead of taking, so what happens that if suppose the current value is W, the gradient value is suppose gradient of F with respect to W. F is the error function, suppose. Then what I will, let me use J because I may be using J later. So suppose gradient J, gradient of the error function. I go in the opposite direction, so I apply minus. And since I don't want to actually make use of the full magnitude of the gradient, but a small step. So a small step here, say 0.001, right? And then I reach here, then I again compute the gradient. I go in the opposite direction of the gradient by making use of an alpha here. So the new weight value will be updated like gradient alpha, gradient J. I hope this point is clear to everyone. If it is clear, please say yes on the chat box or say no. Okay, thank you all. Okay, thank you. So, so that is how it does. So activation functions, I told you, because in computing the error, activation functions, first you will have to take the derivative of, and then only, because if it is like this, right, it is, I take W1 X1 plus W2 X2 plus B, and then I apply an activation function, suppose. So if you have to take the derivative of this with respect to W1, so del J by del W1 will be, first you will have to take the derivative of this and then take the derivative of this part. So you will have to apply the chain rule, and therefore activation functions play an important role here. So a sigmoid activation function is mostly used in like finding the probability whether whether this object belongs to class 1 or class 2 or class 3. So it gives you a probability that given X, what is the probability that it is of class 1, right? So this is the graph of the function. And why it is used? Because its values lie between, 1 upon 1 plus e to the power. Because its values lie between 0 and 1. This sigma z will always lie between 0 and 1. And so it best models the probability function. Rectified linear unit is also one of the most frequently used function, participants. It is used to introduce nonlinearity in the sense that although this is linear, non-linear, this is, I would say that linear, except at x is equal to 0, it is showing some kind of non-linear behavior. Otherwise, it is piecewise linear. So, but it is very much used in introducing non-linearity, because many of the systems behavior are non-linear in nature, and to model the system's behavior, non-linearity has to be also modeled. And so these activation functions help us model the non-linearity in the system. Hyperbolic tangent is another function which is very frequently used, and it is tan hx, which is, you can compute that this is equal to 2 times sigma 2x minus 1. Well, there are many other functions, and people have done research on using different types of functions like leaky ReLU, and there are a lot of functions which are there. I suggest you to go through the literature to find out what all possible different functions are there. Spline functions are also used, wavelets are also used, many other different types of functions are used. So I was telling you gradient-based solutions. So neural networks are usually trained using iterative gradient-based optimization process. And this drives the solution to result in a cost function with a very low value, right? To apply gradient-based learning, choosing an appropriate cost function is important, right? So logistic regression cost function is, we define this as, or generally, it is used for classification, binary classification, where what we do, we take the loss of, just a minute. So it is the, you can see that actual, this was, sorry, this is the actual yi label and the corresponding predicted yi label. I take the loss of prediction by the model that I call as L y hat yi, yi hat yi, and there are m such examples. So JWP is like this. So in case of binary classification, we use this kind of loss function, which is log probability. So I take the log yi hat, yi log yi hat plus 1 minus yi log 1 minus yi hat. Well, this comes from the principle of maximum likelihood. But to just tell you why we have taken this, just see, when suppose the actual label was, it's a binary classification. So the labels will be, say, y is equal to 0 or y is equal to 1. So any sample will be either of class 0 or class 1, right? So if I take, say, y is equal to 1, suppose you take y is equal to 1, right? If I take y is equal to 1, and yi hat, so yi was 1, but yi hat was whatever, yi hat might be 1. So let me take yi as 1. So this is gone, right? This term is gone. You are here, yi log yi hat, right? This is where you are, right? Now, so yi is 1, so I will put, so we are actually trying to minimize the error function, this error function. So let me take just one example instead of m samples now, right? So I am trying to minimize, I'm sorry, I'm trying to minimize I'm trying to minimize log yi hat. Let me take the whiteboard. All right. So I take, I have to minimize log minus log y hat. Think of this, right? Now, remember that y will take value between 0 and 1 because the output is based on, say, a sigmoid function. So sigmoid function value will be between 0 and 1. So y hat lies between 0 and 1. So I plot the graph of log y. 0, 1. So log y will be somewhat like this. I hope you remember the graph of log. So it will be like this. So minus log y will be somewhat like this. Minus log y, right? So when I have to minimize, the attempt is to minimize. The idea is to minimize this error. When I'm minimizing this error, so I just rub this off, right? So I have to minimize this error. When I have to minimize this error, what will be the minimum value? When y hat approaches 1, then log this value minus log y hat will be minimized, isn't it? That means when original signal value, so original label value is y is equal to 1, the algorithm will attempt to reduce the error by making use of some, say, steepest gradient method or any other method. It will attempt to reduce the error by pushing y hat to approach 1. Is that clear to you? I hope that is clear to you. So what I was saying, So what I was saying that here is this, that if y was 1, then minimizing this error means taking y hat to 1. Minimizing this error means taking y hat also to 1. Similarly, you can see that if y was 0, then this error function will help us make y also 0. That is why we use this kind of function, loss function. So in gradient descent, we find WB such that JWB is minimized. Suppose it is a convex function. Although JWB is never a convex function, suppose it is a convex function. That means it has just one minimum. So proceed in the direction of the steepest descent, which is opposite to the direction of the gradient, to achieve the global minimum, right? So the method of steepest descent proposes a new point to proceed to the global minimum, like W prime B prime is equal to WB, where B is a bias, W is a weight, minus alpha, which is the learning rate, gradient of JWB, right? So alpha is called the learning rate, a positive scalar that determines the step size to move toward the global minimum. How to choose alpha? Can somebody suggest a method? How to choose alpha? See, alpha can be 0.1, alpha can be 0.001, 0.005. There are various methods, but generally we take, as practitioners, we choose a small positive number randomly. And then you generally take 0.0001, 0.001, very small alpha. Or the other method is that for each value of alpha, find out what is the value of the error, right, at the new point. This was the old point where you calculated the error. Now calculate the error at the new point, that is J value at this point, for several values of alpha, and then choose the one that gives you the minimum value. This is known as line search, but I've hardly seen people using this kind. So we proceed in the direction of steepest descent to arrive at the global minimum. You have W is equal to W minus alpha del J by del W, B is equal to B minus alpha del J by del B. So until the difference between two consecutive values of the cost function or the error function is negligible, you will keep on making several epochs, that is giving the experience of the data to the machine learning algorithm n number of times, right? That is what is steepest descent method. So let's have a sample of labeled data, that is we call a batch. So suppose you have 2000 samples, you make a batch of say 100, and each batch you forward it through the network, get predictions, and then we back propagate the error for those 100 samples. We update the network weight for those 100 samples. So after we have processed those 100 samples, then we, with the updated weight, I take the next 100 samples. I again forward it, back propagate the error, and then update the network. We keep on doing this until you get a desired level of error. So use error signal to change the weights and get more accurate predictions. Subtracting a fraction of the gradient moves you towards the local minimum of the cost function. Remember, it may not always be the global minimum, right? Whereas in optimization, we seek a point which is giving us a global minimum. So here you can see that there are various optimization algorithms that have been used here. This is the graph of the error function. For different values, it is showing that how the next value of the weight leads to a low value of the error function. Well, there are several types of neural networks, like multi-layer perceptron, the one we just discussed. There are convolutional neural networks, which are most suited for data with spatial characteristics, which has like images or videos, and they can be used. Then there are recurrent neural networks, which are used for temporal data, which is not only temporal, but any sequential data. Yesterday, Professor Beng was talking about linearity, right? Like linear temporal, right? So here, what she took was actually a sequential, which they call as like linear. So here also, instead of taking actually, we take any sequential signal. The sequence can be the sequence of words, the EEG signal, the EMG signal, or it can be any kind of signal that comes, right? So it can be power signal, any kind of signal, which is having a sequential sequence, which is any kind of data which has a sequential nature. So variants of these three basic types have also been introduced by researchers for different tasks. So in summary, this machine learning is a branch of AI in which algorithms are developed that automatically learn the data patterns to take decision. And the type of learning can be supervised, unsupervised, or reinforcement learning. Imitation learning is also emerging as a good alternative to reinforcement learning. Semi-supervised learning is also used when data is not fully labeled. And then I have not talked about support vector machine, which I'll speak in immediately after this. I just wanted to give to summarize about the neural networks. Examples of supervised learning, and neural networks are also used in unsupervised learning. How? Neural networks are used as autoencoders. You know that autoencoders, I don't know if you're aware or not, but autoencoders are a kind of neural networks which learn the data representation. So there is no label that is given. They learn to reconstruct the data or to learn the representation of the data. So it has led to developments in practically all the fields that touch human life, and the game changer has been deep learning. And deep learning, the basic building blocks in deep learning are basically neural networks only. Here I would like to tell you, my dear participants, that the type of machine learning algorithms that we are dealing right now are the neural networks that we are dealing with now are basically, or the machine learning algorithms. They are basically they're basically developed to do a specific task only. Like they're not having the kind of intelligence that humans have. So this kind of machine learning is known as narrow artificial intelligence. Narrow artificial intelligence means they are good at doing one or two tasks only. They're not good like humans to do multiple tasks. You can talk, you can walk, you can at the same time do multiple processing. You're talking to your children, you're talking to your seniors, you're talking to your colleagues, and at the same time, you're also doing many other things, right? So basically sensing that here is some like fragrant, there's something which is good, or various kinds of intelligence that are embedded in a human brain, which are, it is difficult to list out those types of intelligence, like intelligence in terms of mathematics, intelligence in terms of sports, or any kind of intelligence, right? So the kind of intelligence that we are dealing with right now, the intelligent algorithms that we are working on are basically those algorithms which are narrow in the sense they are able to perform only one task very efficiently. They may not be able to perform any other task efficiently. So the next level of machine intelligence, machine learning that we are, the next level of intelligence that we are trying to achieve is known as machine intelligence, right? From machine learning to machine intelligence, where the machine will be as intelligent as the humans, right? In practically, so it's not only limited to one task or two tasks, the consciousness that human mind has, it will be achieving this. So a lot of research is going on in this direction, starting with explainable AI or interpretable AI. And people are working in many different directions to define what is an explainable AI. Well, before I do know, yes, I still have some time to talk to you about support vector machines. But before I go ahead with that, I would like to tell you something about our institute. It's, as you may be knowing by now, that is an institute of national importance established by MHRD, then now it is MOE, Government of India. And we have a residential campus, beautiful residential campus with 250 acres of land. And we have 3 engineering streams, very bright students, mechanical engineering, computer science and engineering, electronics and communication, design, as well as natural sciences. So the references that I have used for this part of lecture is these lecture slides and this book, which I like very much, by GIAN Goodfellow on deep learning. So I would like to stop here for a while and ask you if you have any questions. Please put your questions in the chat box, or you can unmute yourself and we can discuss. Any questions you have? I give a small pause here. So it seems there are no questions. I will start with the support vector machine. Very brief idea I would like to give you. So support vector machine is used in classification regression problem. It was developed by Vapnik and his team at AT&T Bell Lab in 1992-97. It's not very old, but it's a wonderful supervised learning algorithm that has been developed with the idea of the support vector. So I begin with this very small data set, right? Suppose you have two classes in a data set and the data are linearly separable. What do we mean by linearly separable? That if you put a straight line, you are able to separate the data. So can you find a straight line that separates these two different categories of data? You will say, yes, it's very simple. I take a straight line, this. Which line is the best? Is what precisely leads to what we know as support vector machine. There can be several lines that here the data are distant apart.
Slides are not.
Yeah, I'm sorry. Oh, I'm sorry. I didn't share the screen. Okay. 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 Just a minute. Let me share the screen. I'm so sorry. Okay. I hope you can see the. So, as I told that this is the fellow legends like Vapnik have introduced the concept of support vector machine. So I asked you that you have this data, right? If I ask you that, can you find a straight line that separates these two categories of data? Your simple answer will be yes, we have a line. But my question is whether this line or this line or this line. Well, it's difficult to find out unless we have some method by which we can say that, okay, definitely one line out of these is better, right? So the best line that you would like to have, so I have to select the separating line that maximizes the margin between two classes. I'm sorry, two classes means not TOW, TWA, TWO classes, right? Yes, I'm extremely sorry. Two classes. So how to find out the line that maximizes the margin? I have here, I've just magnified this. Now you can see the distance between, if I take this line, or this line, for example. So if I see the distance here and the distance here, this distance is the same, right? Now, if I take, this is the distance, right? But if I take this line, here the distance is quite large as compared to the distance between these two lines, right? So this is a supporting line which is separating samples of class 1 from samples of class 2, or which is, we can say, that is a supporting line which is parallel to the line which is separating the two classes, right? So this is known as the margin. The idea is to maximize the margin. The line that maximizes the margin is known as the best line, right? So, which is known as the decision boundary, the line that maximizes the margin between two classes. And what is a support vector? Those vectors that are at a minimum distance from the decision boundary, like this vector is a support vector, this vector is a support vector. They are from minimum distance from the boundary. What is a supporting line? Like the one I gave you, these, the lines parallel to the decision boundary that touch the support vector are known as the supporting line. And the equation of the decision boundary line can be written like this: Wx plus b. Here W is the vector orthogonal to the decision boundary, right? This one, this vector. I can choose a vector like this, orthogonal to the decision boundary. And supporting lines are, because this line is Wx plus b, so supporting lines will be parallel lines. So they will be Wx plus b is equal to minus k or plus k, right? So these are the equations of the supporting line. Now, finding the optimum margin, that is, you are interested in finding out the largest possible margin, optimum margin. So width of the margin is 2k upon w in norm, right? As you can see, width of the margin is this. And so the main objective is to maximize. So I'm actually normalizing things, Wx plus b, right? So I have normalized by w. So I've normalized by w. So what happens that, like here, you can see Wx plus b is equal to k, say. So when you normalize, you say that x is equal to x plus b upon norm w is equal to k upon norm w. So that is what I'm saying, that we are actually normalizing it. So the main objective is to maximize 2k, like k this side and k that side, right? So that Wx plus b is greater than or equal to k for every x belonging to class 1, and Wx plus b is less than or equal to minus k for every x belonging to class 2, right? So this class, you know that if you have a line, so every point on this side of the line will be having less than or equal to, like if suppose this line is y is equal to mx plus c, right? So for this, it can be y greater than or equal to mx plus c. And here in this part, it will be y less than or equal to mx plus c, right? So exactly this is what is written here. And suppose class 1 is class 1. So suppose class 1 is labeled y is equal to 1 and class 2 is labeled y is equal to minus 1. So finding the optimum margin, right? Finding the optimum margin, we can write it like this, the Wx, now you have samples, all xi's. So what I'll do, Wxi plus b is greater than or equal to k for all xi with label yi equal to 1. And Wxi plus b is less than or equal to minus k for all xi with label y is equal to minus 1. Now I seek your attention, please. This means if I multiply both sides here, this with yi and this also with yi, then this means that if I multiply with yi, Wxi plus b is greater than or equal to 1 for all xi yi, right? So just a minute, give me a minute. Sorry. So that means if, see, this -1 is negative here. This -1 and minus k will make it k, right? So if I combine both of them by multiplying yi on the left and the corresponding sign, you can see that this will actually amount to saying, combining these two will amount to saying that yi wxi plus b is greater than or equal to 1 for all xi yi. So the problem becomes maximize 2 upon w, norm w, or minimize 1 upon 2 norm w square. Norm w1 plus norm w mod, sorry, w2 square and so on and so forth, and then you take the square root. So just to avoid this square root, it's better that we take 1 upon 2 norm w square, right? But then that is not the actually the only reason. It comes from the theory of optimization that this number, this entity comes from a theorem. All right, so the idea is to minimize 1 upon 2 norm w square in this SVM. So let's formulate the problem or model the problem with the hard margin. Hard margin means you have like you're looking for all elements should belong to one side and all elements should belong to other side. And we have sufficient boundary between two classes of objects. So find WB that minimizes norm W square over all xi yi. So you have been given xi, you have been given the corresponding label yi, subject to the constraint that yi wxi plus b is greater than or equal to 1. This is a quadratic optimization problem subject to linear constraints because you've chosen here linear constraints. Quadratic because it's a norm w square subject to these constraints, and there is a unique minimum because there is a unique minimum of this, as we know from the mathematical theory, from the optimization theory. Right, so this is for hard margin. Now coming to soft margin, if I have here some points which are coming close to the boundary, or there are points which are going to the other side of the boundary, question is, which one will you select? You have here a very narrow margin, right? A narrow margin, you have here a very narrow margin line with a very narrow margin. You have a line with a broad margin. So the question is now which one we will select? The answer is I will select still the previous one because this gives a better margin between two classes. Although a number of objects violate the margin or get misclassified. It could be because there is a noise in this data sample. This could be, let's say, misclassified. This could be a noisy, this could be misclassified, but I will still select that. So in order to deal with this, we introduce what is known as a slack variable. So if the data point is between the margin and the correct side of the hyperplane. Hyperplane means this is a line, but in a higher dimensional, it will become a hyperplane. So at the correct side of the hyperplane, I will take this. If it is a margin violation like this, then I will be introducing a slack variable as z is xi greater than 1. And then you can see that xi like greater than 2, here in this case, xi by norm w is greater than this, and in this case, xi is less than this. Okay. So in this case, I model the problem again with an introduction of the slack variable subject to the constraints, here 1 minus xi, and this is a quadratic optimization problem still subject to linear constraints, and therefore there is a unique minimum solution. C here is called a regularization parameter, right? A small c allows constraints to be easily ignored with large margin, and large c makes constraints hard to ignore, right? But then there can be nonlinear boundaries as well. You did not ask me. And nonlinear boundaries, like here, how do we deal with nonlinear boundaries, right? Even for binary classification. What happens that nonlinear decision boundaries give better classification in this case, whereas if I take a linear boundary, although there are a lot of misclassification, but I can choose a nonlinear boundary. So the concept of kernel came into existence. I create a nonlinear classifier by applying a kernel trick. What is the kernel trick? We actually map the data to a higher dimension where it can be easily seen to be classified by a hyperplane using a linear decision boundary, and then I map it back. So kernel function helps avoid computation of explicit data represent instead of directly map to higher dimension, I will be making use of a kernel tree, right? So one only needs computing the inner product between the images of all the pairs of data in the feature space rather than actually finding out a lifting in the higher dimension. This is computationally easier. So let me show you how. So this is the input space. I project it to a higher dimensional space, not project, I would say lift it to higher dimensional space so that now it can be seen. And this is lifting is done through a kernel function. That is the idea. So, no, sorry. So I actually mixed this somehow, and I had to take a different slide for this. So I'm sorry for that. That is all from my side. So today we saw two examples of supervised linear learning algorithms. One is a support vector machine, and the other one is artificial neural network. If you have any questions, you're free to ask. We still have some 6 minutes. Please unmute yourself and ask questions if you have any.